Since its launch in late 2021, the James Webb Space Telescope has already transformed how humanity sees the cosmos. But now, something unexpected is unfolding. The most advanced observatory ever built is returning data that does not simply refine existing theories, it challenges their foundations. Some researchers are beginning to describe it as a quiet crisis in modern cosmology. From galaxies that appear impossibly mature in the early universe to chemical signatures hinting at conditions favorable for life, Webb's findings are forcing scientists to ask a difficult question. What if the early universe was not what we thought it was? It began with faint irregularities buried in deep field observations. Subtle patterns in distant light that initially seemed like calibration errors. But as data accumulated, the irregularities did not disappear. They repeated. In 2023, a research group analyzing ultra-deep infrared scans identified several extremely distant galaxies that should not, by conventional models, exist in their observed form. According to standard cosmology, galaxies in the early universe should appear small, chaotic, and underdeveloped. Instead, these objects showed structured disks, dense cores, and organized stellar motion. Even more troubling, some appeared to contain unexpectedly high levels of heavy elements, carbon, oxygen, and possibly iron, elements that, according to theory, require multiple generations of stars to produce. That alone was enough to raise questions. But then came something even more unusual. Researchers began exploring theoretical frameworks involving exotic early universe objects sometimes referred to as dark stars. These hypothetical structures, powered not by nuclear fusion but by interactions involving dark matter, could potentially grow to enormous sizes before collapsing into black holes. If such objects existed, they might explain why supermassive black holes appear so early in cosmic history. But there is a catch. Dark matter, which makes up the vast majority of the universe's mass, has never been directly observed. It reveals itself only through gravity. And yet, if dark stars or similar phenomena are real, then a hidden layer of physics may be shaping cosmic evolution in ways we do not yet understand. Webb did not stop there. It turned its gaze toward distant exoplanets, including a world known as GJ-1214b, a super-Earth orbiting a red dwarf star roughly 40 light-years away. Long considered a difficult target due to thick cloud cover, the planet suddenly became accessible through Webb's infrared vision. What emerged surprised scientists. The atmosphere contained strong signatures of water vapor and possible traces of methane. While not proof of life, methane is often associated with biological or geological activity. Some models now suggest that GJ-1214b may be a global water-rich world, potentially with vast oceans beneath a dense atmosphere. A world like this raises a deeper question. If such environments are common, how many might host conditions suitable for life? The telescope's discoveries soon extended even further back in time. In one observation, Webb detected organic molecules known as polycyclic aromatic hydrocarbons, complex carbon-based structures found on Earth in smoke, fossil residues, and biological processes. But these molecules were observed in a galaxy so distant that its light began its journey over 12 billion years ago. This means that ingredients associated with life existed long before Earth itself formed. It does not prove life elsewhere. But it does suggest that the chemistry of life is not rare, it may be a natural outcome of cosmic evolution. Then came one of the most surprising revelations: galaxies in the early universe that appeared too large, too structured, and too evolved for their age. According to current models, galaxies require billions of years to grow through mergers and star formation. Yet Webb has identified massive, mature systems existing only a few 100 million years after the Big Bang. Some of these galaxies contain supermassive black holes that, by all known estimates, should not have had enough time to form. One astronomer described it simply: It is as if the universe skipped steps. This has led to two competing possibilities. Either early galaxy formation was dramatically faster than expected, or our understanding of cosmic evolution is incomplete in a fundamental way. And then came something even stranger. Among Webb's ultra-deep field images, researchers identified a nearly perfect spiral galaxy with an unusual feature: its spectral data appeared duplicated. Not mirrored in the optical sense, but repeated in energy signatures, as if two identical versions of the same structure existed with slight shifts in position and timing. Gravitational lensing can distort light, but it cannot fully explain synchronized spectral duplication across separate regions. Some theoretical physicists cautiously suggested an extreme possibility: overlapping cosmological structures, or effects that might resemble interactions between parallel space-time configurations. While highly speculative, the data has not been dismissed. Webb also detected rhythmic patterns in the infrared emissions of a dying star in the Carina region. Instead of chaotic collapse, the signal showed structured pulses, almost like a repeating waveform. When converted into sound, the data resembled a steady, unnatural rhythm. Not noise. Not randomness. Structure. Scientists debated whether this could be a natural resonance in stellar plasma or an unknown physical process occurring during collapse into a black hole. No consensus has been reached. To handle the overwhelming complexity of Webb's output, researchers introduced advanced machine learning systems trained to detect anomalies across vast datasets. One such system identified a region of space that appeared completely empty: no galaxies, no dust, no radiation sources. But within this void, the system detected a repeating gravitational oscillation. When visualized, the pattern formed a rotating structure, not of matter, but of space-time distortion itself. A ripple without a source. A shape without substance. The system labeled it cautiously as unknown structure. Even more unsettling was a separate finding involving redshift data from extremely distant galaxies. In a localized region of the sky, measurements appeared inverted. Instead of older galaxies appearing more redshifted, some seemed to defy expected cosmic expansion patterns entirely, as if time's signature was behaving inconsistently. If confirmed, such an effect would challenge one of the most fundamental assumptions in cosmology: that the universe expands uniformly and time flows consistently in one direction. Some researchers have proposed explanations involving extreme gravitational environments, while others speculate about measurement limitations. A few have even suggested more radical interpretations involving space-time irregularities at cosmic scales. None are confirmed. What is clear, however, is that the data is not behaving as expected. Across all these discoveries, a pattern emerges, not of chaos, but of increasing complexity. The universe, as seen through Webb, does not appear simple or gradually evolving. Instead, it appears active, accelerated, and in some regions, unexpectedly structured far earlier than theory allows. And this leads to a broader realization. The telescope was designed to confirm our understanding of cosmic history. Instead, it is revealing gaps in that understanding. Each answer produces new questions. Each observation introduces new uncertainty. And each layer of deeper vision reveals that the early universe may have been far more dynamic than previously imagined. Some scientists describe it as refinement. Others quietly acknowledge it feels more like reconstruction. Yet despite the uncertainty, one fact remains undeniable. Humanity is witnessing the universe in unprecedented detail. And what it is showing us is not a calm, predictable origin story, but a cosmos filled with rapid formation, early complexity, and physical behavior that continues to challenge established theory. Whether this leads to new physics, revised models, or entirely new frameworks of understanding is still unknown. But one conclusion is becoming harder to avoid. The universe is not simply being observed. It is revealing itself in layers we were not prepared for. And the deeper we look, the more it becomes clear that what we once thought of as the beginning may only be a fragment of a much larger, still unfolding story.